Thank you very much. Are there any questions? Actually, I'm supposed to be Tim Spunk, but Tim's plane arrived at a little after 6.
Tim just go right ahead.
So you're going to have to do it now. I'm filling in for Tim who's not here. So, let me get my notes. It's a deep sky PA. So I'm going to tell you where this beer came from. I made it, actually. I made this beer. That's the short answer. A little longer, it's made from hops and grains and fresh water. I don't know what fresh means. It's billions of years old. Okay? And yeast, living things, right? But more than that, it's made from elements. It's made from hydrogen and carbon and oxygen and nitrogen. And I'm going to put this down. So I'm going to tell you where these come from, because it's where we come from. You and I were made of mostly hydrogen, carbon, nitrogen, and oxygen. I should tell you a little bit about elements. Oh my gosh, it's like class. So an atom has a nucleus, and it's got protons, which are positively charged, and neutrons inside that nucleus. And it's a very tight ball, and there are electrons moving around that nucleus. That's all right? And it's a pretty tight nucleus. If I took that nucleus and I blew it up to the size of a softball, okay, well the nearest electron would be in Belfair. Okay? So it's pretty far out. Alright? The difference between carbon and nitrogen and oxygen is just the number of protons inside that nucleus. If I have one hydrogen or one proton, that's called hydrogen. If I have two, it's helium. You and I were mostly a lot of carbon, right? So that's 6 protons. And nitrogen's 7 and oxygen's 8, and this gold in my ring is a lot more. And where do these come from? In the beginning, 13.8 billion years ago, after about 20 minutes after the Big Bang, it was about 3/4 hydrogen, just 1 proton, and 1/4 helium. There's nothing that you could have made us out of at the beginning. Okay? About 500 or 600 million years after the Big Bang, stars began to form. Clouds of gas began to collapse under gravity. And as you collapse, things get hotter and hotter and hotter. And eventually they collapse down to the point of all this mass. We got temperatures of like 27 million degrees Fahrenheit and pressures of like 250 billion times the pressure we feel right now. Now protons, these charged protons, they're positively charged and they don't like to get together. It's like taking two magnets at the same pole and push them together, they push apart, right? It takes incredible energy to force them together. And if you can force them together close enough, this new force called the strong force takes over, it binds them together. In our sun right now, from what we can see, it's taking hydrogen, single protons, and it's shoving them together under those intense conditions and making helium. But not all of the mass is conserved. As it makes that helium, some of that energy is lost. And that energy is in high energy waves. They're gamma rays that kill you. You know, I know gamma rays with David Banner, made him the Hulk. Actually, they make him a hulky mess. They're not good things. All right? So right now, the sun is fusing protons together to make helium. It takes those gamma rays about 100,000 to 1,000,000 years to make it to the edge of the sun. And then about 8 minutes and 20 seconds to get to us. The sun's going to keep making helium. It's going to take that hydrogen, fuse it into helium until it runs out. But when it runs out, that's bad news for the sun, because the sun, gravity's pulling it in. And that fusion reaction, that heat, those gamma rays, they're pushing back out. And that's what keeps the sun the same size. At some point, in about 5 billion years, I'm going to be pretty old by then, the sun's, the hydrogen's going to run out. And what's going to happen almost immediately, when it runs out, the sun's core will cool off. And that entire sun will collapse down. As it collapses down, it's going to be even more intense. It's going to collapse down, it's going to expand out, it's going to start burning the hydrogen in the outer shells. It's going to fuse that into helium. And it's going to get denser and denser. It's going to get dense enough so that helium is going to start fusing together. Now you're much harder than what the sun is right now. You're going to fuse together, and you're going to take 2 protons and 2 protons, and you're going to fuse them together with another 2 protons, and you have 6 protons. Yeah, 6 protons. You're going to have carbon. You're going to have 7 protons, you have nitrogen. You're going to have 8 protons, you have oxygen. All this stuff that you and I are made of. Alright? Well, how to get to us? That stuff has to be blown out, right? You and I are made of the guts of stars. Now, our star is it's only big enough to fuse up into carbon. And so what's going to happen eventually, it's going to fuse carbon together, and it won't be strong, it won't have enough mass to fuse anything more. And so it's going to be sitting there, this piece of star, used to be the size of the sun, now it's the size of the earth. It's going to be mostly carbon. And under those densities, well, you can take a scoop of it, a teaspoon could weigh about 50 tons. Under those densities, that star, that carbon is going to be diamond. The world's biggest diamonds are dead stars our size. They're called white dwarfs. If they're bigger, a star twice our size, it's going to fuse even more stuff together. It's going to fuse stuff all the way up to iron. Most of the stuff we're made of is iron in our hemoglobin. Now we make humans. These stars have to die to spit it out for us. But now we've got stuff all the way up to iron. Iron's got 26 protons in it. That's the best stars can do. Now, what's left of a star 2 times bigger than us? That's like taking a star twice as big as us and shrinking it down to the size of Bainbridge Island. Now, a teaspoon of that, well, you're from around here, a teaspoon of a neutron star, that's what it'd be. It would weigh the same as 22,000 aircraft carriers. If you just fuse up to iron, well, that doesn't explain some other things. Gold in this ring, it's made of more protons, the atoms are made of more protons than iron. So what happens there? Well, bigger stars, when they die, they have huge explosions. They'll come down from neutron stars and bigger stars. They'll collapse down, and the rebound produces such a big shock wave that it actually forces atoms together and makes the stuff that's heavy in the iron. This gold in my fingers, that was made in a supernova. And perhaps the same supernova that caused the birth of our sun. Silver in my teeth, same thing. The uranium that was nowhere nearby, same thing. Alright? So we're all made of star stuff. I know you've heard this before, but we really are. But not only that, we're proof that stars lived before us. If we look back at the telescope, if we look back further in time, that just means looking out further in space, right? Further out you look in space, you can look back 13.8 billion years. If we look out 10 or 11, we don't see as much carbon, not as much nitrogen, not as much oxygen. It hadn't been made yet. So more and more of the stuff is being made. As more stars are created, the potential for more people like you and me, or more things like you and me, becomes more common. I just want to remind you, when we talk about life around the life of the universe, is there life elsewhere in the universe? Well, we've just started looking. We've already found 31 planets that could be Earth-like. They're the right distance from their star, to the right temperature, hopefully to the right size. The most common things in the universe we're made of. Water is one of the most common molecules. Water and methane and ammonia, they all make us. So we're made of very common stuff. The more we look, the less uncommon we see.